I'll be honest. I was like, hey, what video should I do for my physics YouTube channel? Why don't I ask the artificial intelligence ChatGPT? And ChatGPT said, do a bouncing ball physics problem. And there was something weird in the way they said it, and I can't remember what it was, but I'm going to do this anyway. Okay, so because this does come up, it's a fun thing to do. So you drop a ball, it bounces, hits the ground, it comes back up, it doesn't come back quite as high, and just keeps on bouncing like that. And so let's go ahead and model this. So there's a couple points, and I'm going to make a Python model of this so that we can see what it looks like. And we can make graphs of energy versus time, position versus time, velocity versus time. It's going to be great. So the first part is during this motion while it's falling. While it's falling, it's just projectile motion. Whether it has an initial x velocity vx0 or not, which we will add that in there. It's going to start. Let's say it starts from rest at some height h. I can find at any given time. I can find the position of the ball. And so I'm not going to do a numerical calculation. I'm just going to plot the position. So these are the kinematic equations for projectile motion. So this says that the x position is the initial x position plus the x velocity times time, and the y position is the initial y position plus the velocity, the y velocity times time minus 1/2 g(t) squared. And so this is just for the one fall or one up and down. It doesn't really matter, but not including the bounce. Okay, I can't include that in there because I don't know. I don't have a constant force. There is a way you could put a spring in there, make this interact with the spring, but it wouldn't. It would bounce back up to the same height, which is kind of cool, but I'm not going to do that. So once I do that, then how do I model? What do I do after it collides with the floor? Well, there's a couple ways we could do this. You could say that it loses some energy, a percent of the energy. So I could say, let's call this E1, and let's call this E2, the energy right before it hits and the energy right after. So I could say E2 is 0.8 E1. And so in this case, right before it would have kinetic energy, right after it have kinetic energy in the opposite direction. So I do need to change the direction of the velocity and then calculate this. So let's just say I know the velocity right here, and I can get that up here. So Vy is Vy initial minus Gt. Vx equals Vx initial, right? Because there's no acceleration in the x direction. So, and I can calculate the kinetic energy right before it collides. There's no change in potential energy. So I can say K2 is 1/2 mv2 squared. K1 is 1/2 mv1 squared. And if I set this 1/2 mv2 squared times 0.8 equals 1/2 mv1 squared, then I can solve for v2. So that 1/2 cancels, the 1/2 cancels, and I get v2 equals 1 over the square root of 0.8 times v1. So if I know the velocity right before it collides, I calculate the velocity right after it collides, and then I change the direction. And then I go back to projectile motion. Now, I mean, I don't know that this is actually how balls bounce. I've always seen it done this way, so let's just do it that way and see what happens. If you want to change the code, that's fine. But let's just jump over to Python. We do want to make a couple things. We're going to make a floor, I'm going to make a ball, and we're going to do all this. It's going to be great. Okay, jumping over here to Python. So, if you're not familiar with Web VPython, GlowScript, this is an online Python that allows me to make three-dimensional objects. So let's make this text a little bit bigger so you can see. So the first thing, let's just make a ball, just so you can see how it works. In case you're new to this, I'm going to run that. I'm just going to say sphere. Sphere is a built-in object in Web VPython, and it makes a three-dimensional sphere. You can see that it's right there. I can zoom in and out. I can rotate it around. So that's great. Okay, but I want to make a sphere and a floor. I'm going to go ahead and make the floor first. So let's say floor, it's an object of type called a box. So a box has a couple of parameters. Where is the center of the box and where are the dimensions of the box? So let's make it easy. Let's put the box at a position vector 0. I'm trying to think how thick I want. I'm going to actually shift it down the center of the box so that the top of the box is at y equals 0. So if I have, let's make it a centimeter thick, so then the y coordinate will be negative 0.05, which is that's 5 centimeters. That's half a centimeter down. And then the z coordinate is 0. Now for the size, I'm just trying to think. I want it maybe half a meter wide. So the size is going to be vector 0.5, and then the thickness is going to be 0.01, a centimeter. And then the width, let's make that 0.2. And let's leave it as gray. So let's just run that and see what it looks like. There's my box, see? That's my floor. So I have a floor. Now I need to make a ball. So before I do that, I'm gonna say h. I want to have the starting value so I can put my ball there. Let's drop it from a meter. So h is 1. I'm also going to need this, so I'm going to go ahead and do it. G, my gravitational field vector, 0, negative 9.80. My mass, which I actually don't need. The mass is going to be, I'm thinking of like a ball. A ball, let's say it's 50-gram ball, so 0.05. Okay, now let's make that ball. Ball is a sphere. Its position is going to be at position h in the y direction, so it's going to be vector 0, 0, h, 0. Its radius is that big. Let's see. That's how big my ball is. So that has a radius of a centimeter. 0.01. Let's make it yellow. Color equals color dot yellow. And let's do make trail equals true. So it'll leave a trail behind it because that's just cool. Okay, let's run this. Oh, that's kind of high. Okay, let's put this at 0.3. That's still pretty high. Oh, I changed that. 0.2. I want to change h to 0.3. That's pretty good. I'm pretty happy with that. Okay. So now we're going to go ahead and model the motion of the ball until it falls. Okay. So let's do that. Let's start off. I need some variables. T equals 0. I'm actually going to model the position at different time intervals, so I need to know how much time between my time intervals. So I'm going to call that dt, and let's say it's 0.01. Now I want to keep moving the ball down until it gets to the floor. Now, I actually want let's do this. Okay, I want to look at when y is equal to 0 for the ball. But that's not when it hits the ground, right? Because the ball has some thickness r. So I'm actually going to move this down. Let's move this, that's h. Let's call this r equals 0.01. That's the radius of the ball, and I'm going to put over here r, capital R. And then I'm going to say this minus r, right? So I'm moving the floor down a distance r. So when the ball gets to y equals 0, it hits the floor. And so I can do that. I can say while ball.pos.y is greater than or equal to 0, then do the following. And what I'm going to do, the first thing is to say rate 100. This tells Python to make 100 calculations every second. Since I have a time step of 0.01, that'll run in real time. You can slow it down, you can speed it up, it doesn't really matter. So now what I'm going to do is to calculate the x and y position of the ball, but before I do that, I want to start off with my constants up here. So I'm going to say x0 equals 0, so I should put that x0. Y0 equals h. I left that's fine. Vx0 equals 0. And yeah, I'm doing this the full way, right? Vy0 equals 0. So these are all my initial values. So now I can calculate my x position. X equals x0 plus Vx0 times t. Y equals y0 plus Vy0 times t minus 1/2, which is 0.5, times g times t squared. Okay, now I can move the ball. I want to put the ball at that location, right? So I'm going to say ball.pos equals vector x, y, 0. I didn't do anything in the z direction. I could have given it a z velocity, but I didn't. Now I'm going to update time. T equals t plus dt. So that's all it did. It just ran it until that ball hit the ground. It should work. And I should probably save this. Ball bounce example. And I'm going to give you the link to the code, so don't worry about that. Let's run it, and nothing happened. Cannot subtract a scalar and a vector. What did I do there? Oh, that's where I did wrong. So here I am using the vector g. I'm actually not going to use the vector. Let's just change this to the value g. 9.8. Okay. There, it fell. Okay. So now if I want it to bounce, let's run this. Let's do this. I'm going to print the time it took. Print t equals t seconds. And let's run that. Okay, so it took 0.26 seconds. So I'm going to instead go up here. I'm going to say while t is less than 0.4, right? So that should include the bounce. Now, if I do that, you'll see something that's going to happen. And this is an important point. If I go up here and run it, it just goes straight through, right? It went right through the floor because it's just a computer. It doesn't know what it's doing. It doesn't know that there's really a floor. That doesn't know it's supposed to be a floor. It doesn't know, right? So I have to tell it. So what I'm going to do is after I calculate the position of the ball, I'm going to say this. If ball.pos.y is less than or equal to 0, no, less than or equal to 0, then do the following. Number one, I want to calculate the new velocity. So let's go up here and call this c equals 0.8. That's my coefficient of how much energy I lost. So I already said what would happen. I said v equals the square root of 1 over c times v. So that might look weird, right? I don't have v. Let's see. Let's calculate. Vx equals v. That doesn't change. Let's go Vx equals Vx0. I don't really care. Vy equals Vy0 minus g times t. So now I'm going to say Vy. I should do this the full way, right? So then V equals the square root of Vx squared plus Vy squared, right? Because that gives me the total magnitude. So now the new velocity is going to be the old velocity times this coefficient right there. And so it may look weird that these v's would cancel, but it doesn't, because this is not an equal sign. This is a make equal to sign. This says take the value of v, multiply by the square root of 1 over c, and then make that the new value of c. So I changed it. Now I need to set my, oh boy, this is going to be tough, because I need my velocity, my Vx and my Vy. But I don't know if it would be the same. I'm thinking if both of those change, then the angle could change. Well, so Vx, I wonder if I could do that. Let's just try this. Not do this. I'm not sure this will work, but I'm going to do it anyway. So let's say Vy equals Vy. I think that the decrease in the x component of the velocity depends on friction, but that's a more complicated case. Let's just do it this way. Vx equals Vx square root of 1 over c times Vx. So what I've done is decrease both of those. Now, I also want that y velocity to be going up. So I'm going to change this to negative. So if it was going down, which it should be if the position is less than 0, now it's going up. I think that should do it. Let's just see what happens. Nope. Why didn't it? If the ball... Aha. And that's what I need to do. I changed the velocity, but when I went back up here, I didn't change this. This still says I don't care what it's doing, right? So what I'm going to do is now I have a new projectile motion problem such that Vy0 is equal to Vy and Vx0 equals Vx, and then x0 equals 0, y0 equals 0, right? So now I'm going up. I think that will work now. It's a new projectile motion problem. Ooh, something weird happened. I think do I need to put t is equal to 0? Yeah. Oh boy. Okay, new plan. Let's just model this numerically. Yeah, I think it'll be okay. Switching back to vectors. Because what I need to do, I have a problem at that time, right? Because if I change the velocity and change the initial position, I need to change the initial time. And I guess I could do that. Let's see if I can do that. 9.8. I'm going to actually have two times. I'm going to have the real time and the bounce time. So let's say BT is equal to 0. So down here, this is going to be BT. BT, 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 BT. And that's all fine. And then I'm going to increase BT. BT equals BT plus DT. But down here, the bounce time is going to start back over at 0 too. BT equals 0. I think that will work. There. Oh, but when is just as high? Oh, because I didn't. Oh, why did it go just as high? V was negative square root of 1 over c. This is being more complicated than I want it to be. What if I just say that's going to be a number, that's the new velocity, v2, is equal to the old velocity times, I think this should be this. Yeah. Okay, so it didn't bounce up as high. Okay, I'm good. So let's do, what if I just run this for 4 seconds? I did it. Okay, I'm pretty happy with that. There you go. Now, I don't like that line staying up there. I can fix that. Let's see. Let's go up here to GlowScript. I can't remember how to do this. Retain 50 is something like that. So go to Help, Work with 3D Objects, Graphs, Make Trail, Make G dot, Add Trail, Retain, Special Options, Dot equals true. No, it's dot. Oh no, this is no. This is not a graph. This is a attach a trail right there. Points, retain 50. Let's do that. I'm going to copy this whole thing. Copy that. And then I'm going to go back over here to this. I'm going to add that on here. You can press return. And let's see what that does. Okay, that's not too bad. Retain fewer. Let's see, let's retain 10. And this is just for looks. Okay, that's not so bad. Okay, what I want to do is I want to make a graph. I want to make a graph of position versus time. I want to make a graph of velocity versus time, and a graph of the total energy as a function of time. That will be fun. And then I'm going to go back and I'm going to give it some horizontal velocity. So let's make a graph. So up here to make a graph, I'm going to say G1 equals graph. let's just give it an X title. This is going to be position versus time. So the X title is going to be equal to time in seconds. The Y title is going to be equal to Y in meters. And I'm going to give it the size. So I'm going to say this is equal to, has a width of 500 and a height of 150. I'm going to make it skinny because I'm going to have 3 graphs right there. So in WebVPython, if I had to make that graph, I need to make a function. If I put the function right below the graph, it'll go to that graph. So I can say FP for position is a type G-curve, color equals color.blue. And let's just make that one graph. So then down here, what I want to do is to plot a point. So I'm going to say fp.plot t, the total time, and the position, which is going to be equal to y. I think that should do it. There. That looks good. Okay, now we're going to make a velocity graph. So up here, I'm going to say a new graph. I'm going to put it below this line right there. G2 equals graph. X title equals V in meters per second. Y title equals, no, this is V in meters per second. That's T in seconds. And Y title is V. And then width, 500, height, 150. And FV is G curve. Color equals color dot red. Now down here, I'm going to plot the velocity. This is actually the y velocity. So I'm going to say FV dot plot T YV VY. Okay, excellent. So it starts with the 0 velocity. It falls down and decreases. Then during the bounce, it just jumps up here to the same, well, not the same, but a smaller positive value. And then it just keeps bouncing up and down and down. That's pretty good. Okay, now we're going to plot 3 things: the total energy, the kinetic energy, the potential energy. And then we'll be done. So up here, I should save that. And let's go to edit code. And I'm going to add one more graph. So G3 equals, I'm going to copy this. And I'm going to say that, and this is just going to be energy in joules. And then I need 3 curves in here. I need the kinetic energy, Fk, capital K. Fk equals G curve, color equals color dot blue, Fu equals G curve, color equals color dot red, and Fe equals G curve, color equals color dot green, even though the green never shows up really well. Let's do magenta. Magenta. Okay. So now I need to calculate those 3 things before I plot them. That's not too hard to do. So I'm going to say K equals 0.5 times M times V. This, I will do the total velocity. V x squared plus Vy squared. The potential, U, is M times G times Y. And then the energy is K plus U. So now I can plot those. Fe dot plot T E, Fk dot plot T K, and Fu dot plot T U. Let's check it out. Okay. So here, is that right? Yeah. So up here, you'll notice that during the fall, the total energy is constant. But then after it hits, it has a decreased total energy and a decrease and a decrease and decrease. Okay, let's try something. What if it loses 50% of its energy after every bounce? So if I go up here, I can just change. This is just for fun. So I'm going to change C. Where's my C? To 0.5. Okay, excellent. I like that. Now, there was a question that said, Actually, the chat AI asked this. It said how many bounces till it stops, and the answer is infinite. Right? It's never going to stop because every time it bounces, it's going to lose more and more energy. Now, you could say once it gets to a certain point, I'm just going to call it stopped, but it would technically never stop. I wonder if there's a way you could have an exponentially decreasing energy. I'm not really sure. Okay, let's do one more thing. What if it has some initial x velocity of 0.1? Let's just see what that looks like. Oh. What did I do? That was not right. Oh. That's weird. Vx0. Vx equals Vx0. Vx0. Okay, I'm not going to mess with that. I don't know what I did wrong. I don't want to mess with that. I got a good thing going here, so I'm going to save that and end this ball bouncing model. Okay, so again, I'll put the code down below. Hope you enjoy that. I like the graphs. If you don't like the graphs, that's cool, but that's that.